Susan hasn't tested the query yet, so she'll save the query in My Queries and then test the query before she shares it. Now, Engineering Lifecycle Manager Product Documentation. Susan will copy the code for open ECRs assigned to Susan. She'll paste the code here. The query contains colorized comments to help guide you to places where you can customize the code for your use. For example, you might need to query for work items of type defect, so you'll change that here. You'll also want to change the query name here to your own. Notice that you can change the status of the change request you are querying for here. Click Create, and then run the query. Look at the query results. Be sure the query returns the results you expected. If not, go back into the query to edit it by clicking the Edit Query icon. If the query returns the expected results, you can share the query with your team. Susan's happy with the query results. Her team lead has asked her to share the query so he can keep up with her open ECRs. The query Susan created is now in My Queries, so she'll copy it to Shared Queries. Susan will copy the query so she can keep a private copy in case she needs to change and test it later. Now Susan's team lead can run the shared query by clicking it. If Susan wants to use the query to create a custom view, she can do that too. Thank you for watching this video.
Okay, thanks, Mark. All right, so I'm going to advance the slide here to the agenda. So what are we going to talk about today? We'll start by talking about how to unlock engineering knowledge and the need to do that. We'll talk about unliberated versus liberated engineering data and what that means. And we'll talk about the complexity in today's smarter products and the various different integration approaches you can take to managing the multiple tools that you deal with. And then we'll talk about some of the things that have led up to the development of Rational Engineering Lifecycle Manager, which helps to solve some of the problems that we'll talk about. So as we get into the discussion about Realm, we'll talk about the Internet as inspiration for the development of the product, the importance of linked data, as well as the open services for lifecycle collaboration protocol and how that's used. And then we'll talk about more of the features of Realm, and we'll have a little bit of a demonstration at the end. So continuous engineering, you may have heard about this. It's a vision that we hope you will help us create. So how would engineers like to work in an unconstrained world without the boundaries of geographies, different disciplines, different silos? How would you work and do engineering without any boundaries? If you think about that, that helps you kind of think about the way we want engineering to work. And if we back into continuous engineering by first looking at discontinuous engineering, this is what we deal with today, where there are gaps, discontinuities, stops, breaks in the engineering process. So when you have to stop and look for information and you have to hunt around, that's a discontinuity. It breaks up your work to go out and look for something, dig around, hopefully find what you're looking for. And it's work that has to be done, but it's not front and center to what you're trying to do. So if you have to investigate and explain things over and over again, that's a waste of time. Continuous engineering minimizes that kind of work, that peripheral kind of work, and it makes information easily accessible so you can make informed business decisions. Now, continuous verification, the next bullet here on the slide, that's the second in one of three pillars of continuous engineering. And continuous verification implies testing early and often. Strategic reuse, which is the third pillar, that's a high-level business strategy to reuse assets. So it makes good sense to reuse assets. Strategic reuse makes it a planned process across an organization. So it's at a high level in a company. If you want to find out more about continuous engineering, we have a great book. It's called Continuous Engineering for Dummies, and it's downloadable at the URL here on the slide. Unliberated engineering data. Here's some data. 4.49, 6.5. But what does it mean? What do I do with it? How do I figure out the relevance of that data? People get a partial view of something, and then we need to spend some time tracking down answers. This data doesn't have context. It doesn't have meaning. So we need to go looking for more data. So when you get data that's incomplete, you have to do the work to find some context to help you make sense of the data. Data alone is not enough. It needs context, it needs meaning, it needs interpretation. So we call this unliberated engineering data. Now, let's say you manufactured a car, and it had an ignition system. There's our little ignition there with the key. And we see there was a requirement for the vehicle power mode. And the power mode of the vehicle is driven by the ignition state. The ignition states are off, accessory, and run. A requirement is driving the ignition design. That same requirement is driving the design of the deployment of the airbag. The airbag doesn't deploy when the vehicle isn't moving. So you have one part of the organization, you have somebody developing the ignition system, and you have somebody else developing the airbag. Different parts of the organization need to know what the other is doing. So the person developing the airbag needs to know what the guy developing the ignition is doing. But in big companies, there are silos, and there are risks inherent with the discontinuity. And you can understand this even if you're not working for an automotive manufacturer. Same type of thing happens when you're building a plane. So in this example, when the ignition switch was changed, meaning the engineer changed it, so less force was required to move between the different ignition modes. The problem was that this new design didn't meet other specifications. The ignition flipped out of running and into off. The supplier said the ignition did not meet the specs, but there was no formal change process. The engineer made that change and moved forward. He didn't think about what impact it might have on the other parts, like on the airbag system. Had he known that indirectly he was impacting the airbag deployments, he may have taken more care in changing the design. So what happened was that when the engine shut down, the airbag stopped deploying, and that had a catastrophic result that wasn't expected. So what about the safety standards in this case? ISO 26262. That's the safety standard for automotive, and the best practices for developing systems to meet those safety standards. The engineer, when he changed that ignition system, he wasn't thinking about the downstream impact of that change. He didn't do an impact analysis. He probably wasn't able to. An analysis of the impact of the change to the ignition system would have indicated that that airbag system needed to change as well. So that would have been helpful in this example. So the point I'm making is that information is important, and finding information easily is important. Research shows that a lot of knowledge workers spend time searching for information, and in many cases the information isn't found. This leads to rework, can lead to recreation of information, can lead to abandoning searches, so round and around it goes. This affects engineers and engineering data, and the net is that engineering teams are spending a lot of time on unproductive tasks.